In terms of natural resources, it is unlikely that the Earth can support an ever-growing population with progressively higher living standards forever. By giving man the necessary exploitation and transportation systems, he can make the entire solar system his raw material source and cultivate Earth as the biological center of a growing mankind. Initial studies of the first manned flights to Venus and Mars during the early 1970s have revealed the need for an ambitious program. History shows that such ambitions can be realized. The first age of discovery began when Henry the Navigator covered 1,200 miles between Portugal and the Azores. Only 90 years thereafter, Magellan had circled our world. Our present age of discovery began 4 centuries later. Now we have progressed to a point where we expect to reach the moon in this decade. Limited manned interplanetary flight can then come in the 70s. By the end of the 80s, we should have covered the entire solar system with instrumented probes. This then offers the realistic possibility that a Magellan could reach Pluto by 1995, just 53 years after the first large-scale rocket flight. This may be considered part of the answer to why we should now be preparing to develop manned interplanetary flight capability. Then come the questions, what do we want to do, how, and when? Our first objective is to demonstrate by actual accomplishment the feasibility of manned flights to Venus and Mars. We want to conduct low-altitude reconnaissance of these planets. In summary, we want to lay the foundations for the manned landing expeditions to follow. We have a choice of 3 mission types. Flyby, where we simply make a hyperbolic encounter with the planet, pass through its activity sphere, and return to Earth. Capture, where we stay near the planet as a satellite for anywhere from 10 to 50 days before returning. Detailed planetary reconnaissance involves many types of auxiliary vehicles. For example, for Mars we have studied mappers, floaters, landers, and returners, 2 of which also serve as Mars excursion vehicles for an optional, limited manned landing operation if judged feasible by the expedition. The Martian moons will be explored by separate probes. The third choice, of course, is surface landing involving a major assault on the planet with longer stay time and mobile exploratory capability. In terms of overall effort, the difference between flyby and capture is small. The same ships, the same unknowns, and the same risks are involved. Capture is somewhat more expensive, energy-wise, than flyby, but yields the greatest return in terms of information and progress toward a major landing mission, which must be the ultimate objective. So our study is primarily based on the capture mission, where landing is possible but not required for mission success. Facts and trade-offs are established, iterated, and reiterated until they can be integrated into a balanced program. Among the criteria are planetary constellations versus schedule, energy requirements versus propulsion systems, mission periods, and perihelion distances, weight considerations versus radiation shielding requirements, capture period, and auxiliary vehicles, orbital versus interorbital vehicle assembly versus launch vehicle requirements, crew emergency capabilities versus Earth rescue capabilities, and finally, mission flexibility, reliability, and overall economy. This calls for integration of the planetary into the total national space program, especially the orbital and the lunar programs for their mutual benefit. Now, we have constructed maps for the interplanetary navigator to use in charting his course to Venus and Mars during all suitable constellations in the 70s. The abscissa shows the Earth's departure and arrival date, the ordinate, the target planet, arrival and departure date. This date is offset with respect to the abscissa by the minimum transfer time Earth to target planet considered. The two dates are matched along the equal date line. These lines here represent lines of constant transfer period from Earth to target planet, these from target planet to Earth. By selecting an Earth departure date and a transfer period, the transfer orbit to the target planet is defined in terms of its orbital elements, transfer angle at a t, and hyperbolic excess velocity at Earth departure and target planet arrival. Thus, the first portion of a given mission profile is defined by connecting a selected departure date with a given transfer period. Our capture period is measured here. The return orbit is again defined by selecting a target planet departure date and a transfer period for the return flight. Now the complete mission profile is defined. On the mission map, the profile is represented by this line. For each date instant, there is an infinite number of transfer orbits of varying periods. Selecting discrete dates and transfer periods, we obtain a number of discrete one-way orbits, out and back, each represented by a dot on the T1 or T2 line. Some of these orbits are more, some are less expensive in terms of transfer energy, either for Earth escape and target planet capture, or for target planet escape and Earth recapture. Not only does the absolute energy level vary, the energy distribution between Earth escape and target planet capture, as well as that for the return transfer, varies also. For an Earth-Mars round trip in 1973-75, this energy pattern results. Obviously, the wide variation of energy levels imposes constraints on the feasibility of certain mission profiles. Some waters are just not navigable in the early 70s because the available propulsion systems are inadequate. These regions, then, yield the most desirable profiles for that time. An additional constraint is imposed by practical limitations in minimum solar distance during the mission. For the present, we assume that perihelion distances of less than 0.6 astronomical units will be avoided except in emergencies, and that, on the other hand, the ships are insensitive to danger down to 0.9 astronomical units. For Mars, we have avoided perihelion distances of less than 0.8 astronomical units. This, then, is a distribution of the intermediate regions. Here we see that most of the desirable energy regions do not coincide with regions of dangerous heliocentric distances. In many cases, we do not pass through the perihelion at all, so this constraint is not involved. So, here at a glance are the Earth-Mars mission windows for 1973-75. This is the most desirable Mars period in the decade. In 75-77, the conditions are comparatively less favorable. In 77-79, the energy requirements for fast reconnaissance missions are very severe. But if we could capture during the 73-75 period, we would now be prepared to take advantage of these conditions. Here could be our first major landing, where we would not have to worry about immediate return and thus avoid the high energy requirements connected with this constellation. Our stay time would now be approximately 360 days with a very inexpensive flight home. At certain constellations, the transfer orbits are steeply inclined with respect to the ecliptic. To avoid the associated high energy requirements, it is necessary to make a plane change en route. This raises the number of major maneuvers during one transfer to 3. The practical implications of this depend mainly on the type of engines available. Constellations of this type are rare. Between 70 and 75, Venus offers more favorable conditions in terms of both reduced energy requirements and mission period. In addition, the Sun is quiet, making Venus runs all the more attractive. During these constellations, mission velocities for Venus are roughly 60 to 85% of those for Mars. Mission periods are generally 1 year or less for Venus and range from 370 to 450 days for Mars. The how is dominated by two major questions. We don't know just what mission lengths man can stand, so we have selected the shortest trips consistent with mission objectives and propulsion energy. Propulsion is the second question. Our mission capability will be profoundly influenced by whether we have a metal carbide reactor engine of high mission versatility and long lifetime. The best approach involves a highly modularized ship with a high-thrust nuclear escape booster and an interplanetary ship. With a crew of preferably 8 persons, the expedition would be flown by a convoy of 1 crew vehicle and 1 or 2 service vehicles that serve as spare crew ships and carry propellant reserves, spare parts, and most of the auxiliary vehicles. To reduce crew risk and standardize parts and operations, this concept is based on complete interchangeability of propellant tanks, life support system modules, and other essential subsystems. In this phase, the escape booster and the interplanetary ship are handled and checked out as separate units. The escape booster requires a thrust of about 700,000 pounds, which could be generated by either one 700K engine or 4 Phoebus engines clustered 25 feet apart to prevent excessive reactor interaction. Specific impulse would be about 845 seconds. The interplanetary ship has a mission engine of 30 to 50,000 pounds thrust. A spare engine is included. Both units are mated in the launch area for composite checkout and systems testing. Since vehicle sizes vary with planet and with planetary constellation, the tanks are custom made for different missions. The modular vehicle design takes this requirement into account. Prior to launch, the units are demated, fueled, and otherwise made operational. Transported into orbit by a post-Saturn vehicle of 750,000 to 1 million pounds payload capability, they are mated again and flight readiness tested. So assembled, they are self-sufficient for the entire mission. Orbital mating of such massive units can be avoided if the crew vehicle is carried to the planet in 2 sections, one being the life support system and Earth capture module, the other the target planet escape module. So each section would be launched into departure orbit as payload of a complete vehicle with Earth escape booster and target planet capture module attached. This mode then requires mating operations in the target planet capture orbit. The life support system, protected by 11,500 pounds of polyethylene shielding, is highly modularized. Here we have 4 mission modules containing 4 two-man rooms, an observatory, food, sanitation and storage facilities, a gymnasium, a scientific and medical lab, library and recreation area, and a repair shop. The heart of the life support system, the command module, is immersed in the Maneuver 4 hydrogen tank. Containing all control and other key equipment, it also serves as a radiation storm shelter for the entire crew by virtue of combined polyethylene and hydrogen shielding. A utility shaft with a system of airlocks provides access to the mission modules, 2 space taxis which are used for inter-vehicle travel and module exchange operations, and to the 8-man Apollo-type Earth entry module. Front sections of the service vehicles carry auxiliary vehicles of comparable weight. Only one accompanies the cruise ship back to Earth. Now it has almost no payload, but enough propellant to carry the crew and its life support system during the target planet escape and Earth capture maneuvers in case the original crew vehicle is incapacitated. The life support system, except the Earth entry module, is jettisoned prior to Earth capture. The orbital energy of the cruise ship is then reduced to a slightly negative value to retain Earth capture, giving expected Apollo conditions for atmospheric entry. This is the weight distribution of a self-sufficient crew vehicle for a typical reference mission to Mars in 1973. Now, assuming Mars for the first capture mission and taking 1973 as both the easiest constellation and a prerequisite for major landing later in the decade, we have been asked to investigate the aspects of preparing for that mission. This schedule, covering all directly and indirectly involved key requirements, is an example of what would have to happen if the 1973 date with Mars were to be met. A great number of basic decisions on which to base the planning must be firm in 1964, particularly the choice of nuclear engine and mission mode. Using the convoy vehicle as pace setter, pre-design should be complete during the same time, while basic testing proceeds to lay the foundations for experimental design, which continues parallel to experimental testing and is complete by mid-66. Final design requires specification of all important subsystems here, and data from supporting space research programs, interplanetary probes, for example, are fed into the system. The ecological and life support systems must enter design and hardware phases by mid-64 to provide the necessary specifications by mid-66. Component testing proceeds parallel to final design. Following ground test, the life support system is tested in orbit, providing at the same time a manned space laboratory. Test articles and prototype modules are manufactured during the 67 through 70 period. Subsystem hardware must be delivered during this time. Test articles and prototype modules are concurrently ground and orbit tested. Changes resulting from evaluation of the tests in 68 and 69 can still be incorporated into the operational system, which enters production in mid-1970. In late 71 and the first half of 72, the crew and the prototype vehicle have a final operational rehearsal. Running 2 or 3 lunar capture missions involving cislunar and translunar flight paths, they simulate all essential features of the interplanetary mission and at the same time deliver life support systems for the first lunar base. Any significant deficiencies uncovered during these flights could not be rectified in time for the 1973 Mars capture, postponing into 1975. But assuming the rehearsals are successful, the road to orbital departure of the convoy in April or May 1973 would be clear. Since we assume that at least 2 convoy ships will be launched, at least 3 ships must be brought to orbital flight readiness involving 6 launches. If they are 75% successful, a total of 8 main launches is required, plus several supporting launches of smaller vehicles for personnel transport, repair, and miscellaneous tasks. With 1 launch per month from each of 3 complexes, delivery of all vehicles is accomplished inside 3 months. A total of 100 days from first launch to orbital departure is postulated. This time is slightly more than 20% of the mission period proper. It can be reduced and the confidence level in its realization increased by the use of offshore launch facilities. In this case, spare launch platforms can quickly replace a platform destroyed by a launch failure, or spares can be thrown in to increase a launch density if necessary. Obviously, this schedule is very tight, requiring unprecedented discipline and success in its execution. Its purpose is to show that a strong sense of urgency is required if we are to try for Mars in 1973. This program adds a considerable load to the strain of the lunar and post-Saturn launch vehicle programs. In view of the resulting stress on manpower, funds, and facilities, the chances of missing the 1973 Mars mission windows are very strong. However, there are several things we can do about this situation. First, we can work toward a fully integrated national program for manned spaceflight, taking a modularized approach to space station, lunar, and Venus-Mars programs. They are not separate or even competitive programs. They can be handled as individual combinations of common elements. Our present and future efforts towards standardized instrument units, guidance, communication, and power generation systems can be complemented by standardizing space vehicle sections and space vehicles for use in all 3 programs and for as many missions as possible. Life support system and nuclear-powered interorbital vehicle development are cases in point. The life support systems for, say, an 8-man space station, an 8-man first-generation lunar base, and an 8-man fast reconnaissance ship to Venus or Mars are enough alike that we could plan the development of a single, long-duration life support system for use directly or with some modification in all 3 programs. Nuclear-powered space vehicles are a real necessity for cislunar transportation and manned planetary flight. The NERVA engine spearheads the important development of a nuclear rocket engine technology. Subsequent efforts are expected to concentrate on improving thrust, specific impulse, and operational versatility. This should lead to an advanced NERVA with higher specific impulse and to an engine of higher thrust and higher specific impulse. The latter would use a reactor of the type designated Phoebus by the Los Alamos Scientific Laboratory. For still higher thrust, Phoebus reactor engines could be clustered, or an engine of about 4 times higher thrust could be considered in lieu of the Phoebus engine. From the vehicle systems viewpoint, the latter would be more desirable for the Earth escape booster of an interplanetary ship, primarily because it is lighter than an engine cluster of equal thrust. Second, we must carefully examine all alternatives to the 1973 Mars capture mission. The first alternative is to continue to consider Mars as the #1 target planet, but to postpone the first capture mission to 1975. As in 73, the 1975 Mars mission requirements lead to large ships which, for all practical purposes, call for the availability of a post-Saturn Earth launch vehicle. But now we have added 2 years. This greatly reduces the burden of Earth launch vehicle development schedules. We also stand a better chance of getting a metal carbide reactor mission engine, which would more than compensate for the increased energy requirements of 75 over 73. Postponing capture to 75, however, would probably mean the abandonment of a major landing expedition to Mars in the 70s, requiring launch in October-November 1977. This leaves insufficient time for data reduction and evaluation of the 75 capture. The next opportunity would be in November-December 1979. In 79-80, we must expect a new peak in solar activity, which may force a temporary pause in manned planetary missions, except perhaps with vehicles like Orion. The second alternative is to consider Venus as first target planet with which to demonstrate the technical and operational feasibility of planetary capture missions. A 1973 mission to Venus is quite compatible with the solar cycle, since solar activity should be at a minimum. Venus requirements are lower in terms of both mission energy and mission period. For comparable capture periods, about 30 days, a Venus ship of equal initial payload weight and propulsion system will weigh between 30 and 50% of the corresponding Mars ship. Now it becomes possible to consider Saturn C5, perhaps with slightly uprated F1 engines, as principal launch vehicle. This then would disengage the first interplanetary mission from the post-Saturn ELV development program. Using Venus for the feasibility demonstration, it is still necessary to conduct detailed reconnaissance of Mars to define a landing site. But large and rugged instrumented probes could furnish this information with a high degree of reliability by 1975. With both prerequisites thus accomplished, a major Martian landing expedition could be planned for 1977. The study so far has produced considerable amount of results which are reported separately. 5 principal conclusions and recommendations can be presented here. First, comparisons have been made of different types of manned planetary vehicles. The results show quantitatively that nuclear propulsion in any form is superior to chemical drives for the missions considered, not only with regard to vehicle size and performance, but to launch vehicle requirements and required level of orbital pre-departure operations. The study has also shown the advantages of providing the planetary ship with a nuclear mission engine of ready restart capability and long operational life. It is suggested that the potential of metal and metal carbide fast neutron reactors for engines of the 30 to 50,000 pound thrust level be fully explored. Second, if any manned interplanetary flights are to be achieved in the 70s, their planning and preparation must be integrated into the National Space Program within the next few years. In particular, it is important to conduct an intensive study program on suitable post-NERVA engines. This would provide the information and recommendations required for a decision, as soon as the NERVA program has progressed adequately, on the second generation nuclear engine using a reactor of the feeblest power level or higher. A decision on this engine and its development schedule is perhaps the most important single input into the systems planning of manned planetary flights for the first half of the 70s. Third, initially, that is during the 70s, it appears neither practical nor advisable to plan Venus or Mars missions at a faster rate than every second departure constellation. Otherwise, the results of the preceding mission could not be evaluated in time to contribute to the subsequent flight. For Mars, then, the earliest mission following a 1973 departure would begin in 1977. For a 1975 departure, the next flight would be in 1979. Venus departures should be planned for 1973 and late 76, or for 1975 and 78. Increasing solar activity in the second half of the 70s may well endanger the feasibility of Venus runs later than 1975. The same applies to Mars, with the additional adversity of increased energy requirements for fast Martian missions during the 70s and early 80s. This is because the position of Earth-Mars oppositions moves away from the nodal line of the Martian orbit, causing transfer orbits to be more steeply inclined with respect to the planes of the planet orbits involved. For these reasons, conditions become appreciably less favorable for at least 6 years following 1975 until the solar activity subsides. Fourth, these facts show that it is worthwhile to attempt the first manned planetary flight in or before 1975. In view of the lunar task ahead, it appears unrealistic to plan a planetary mission prior to 1973. On the other hand, Mars, even in 73 and 75, requires appreciably higher mission energies than Venus. If a post-Saturn vehicle cannot be counted on for 1973 and is marginal for 1975, a Venus capture mission should be considered seriously for 73. Using a Saturn C5 as ELV and keeping the orbital launch weight of the individual Venus ship inside 1 million pounds. This can be achieved even with a combination of NERVA and oxygen-hydrogen engines, without losing the capability of capture and re-escape around Venus, provided the capture orbit is elliptic rather than circular. Since a first Venus mission may not include an optional surface excursion capability, an elliptic orbit is more readily acceptable. Fifth, using moderately elliptical capture orbits with an apoapsis distance not more than 4 times the periapsis distance, which is assumed to lie about 1,000 kilometers above the Martian surface, and allowing orbital departure weights for chemonuclear convoy ships up to 1.5 million pounds, Mars could also be considered for 1973 or 75 in conjunction with Saturn C5 as ELV, without necessarily losing optional surface excursion capability.